Okay, so these are the linear programming problems on the worksheet that I gave out last week. I'll give you a second to read this first one. Maybe pause it if you need to read it. Okay, so here's the solution for the first one. We're organizing the information. There's cups and plates. Each of them take a certain amount of time to make in minutes and require a certain amount of pounds of clay. And in this case, we have a certain amount of time and pounds of clay, total pounds of clay available. And then you have the profit from each of them. So what we're trying to do here is maximize the profit. So the question asks, how many cups and how many plates should make in order to maximize the profit? What is the maximum profit? So our objective function is the profit, since each cup, if x is cups and y is number of plates, if each cup has $2 profit, plate $1.50, then objective function is going to be 2x plus 1.5y. That's the profit. The constraints, usual x and y bigger than or equal to 0. 6x plus 3y less than or equal to 1200. That's just saying that the total time available is 20 hours. So I put everything in terms of minutes, so I converted the 20 hours to minutes. 3/4 x plus y less than or equal to 250. That's saying that we have 250 pounds of clay available. And what I like to do with these is reduce all the common factors and then get rid of the fraction. So on this one I divided through by 3 to make that into 2x plus y less than or equal to 400. It's a little easier. And 3x plus 4y less than or equal to 1000 multiplied through by 4 to clear the denominator. Just makes it easier to graph the feasible set. So you graph this system of equations. 2x plus y less than or equal to 400 has y-intercept 400, x-intercept 200. So that is this line right here. 2x plus y equals 400. 3x plus 4y equals 1000 is this other line right here. And since this is less than or equal to, we end up getting this polygonal region with one corner at the origin here. So the vertices are the origin. These two intercepts, this ends up being the intercept 250. This is intercept 200. And to find where they meet, you have to set the two boundary lines equal to each other. So I just did substitution. You can read through it down here. If you do substitution or elimination, you'll get the point 120, 160. So the last step, we're going to list all the vertices because the maximum has to occur somewhere at one of these vertices. Evaluate the objective function at each of the vertices. So 0, 375, 480, and 400. And not surprisingly, the maximum profit comes from a mix of the cups and the plates. Not going to be all cups, making all cups or making all plates, but a mix of the two. So $480 occurs when you make x is 120, so you make 120 cups and 160 plates. Always be sure to write your final answer in the form of a sentence there. On the exam Wednesday, what I'll have is I'll either have you do like half of the problem, so setting it up, so you're given the word problem, you'd have to get to, say, this part right here with the objective function and the constraints, the variables, objective function, constraints, or I'd give you the linear programming problem here and ask you to figure out where the maximum or minimum occurs. Okay, for number 2, let me bring that up. Okay, so if you need to read that, you can pause it. How many of each type of refrigerator? We're trying to maximize profit again. The thing here is at least 50 refrigerators in total must be sold, so that's a little bit different constraint. We've got large and small fridges. Really the only constraint here we're looking at is the cubic feet and the fact that we need 50 in total. So the 50 doesn't really factor into this table that we're making here. but it does factor in down here. X and Y, number of large and small fridges. Since the profit is 250 for each large fridge and 150 for each small fridge, 250x plus 150y. Constraints, the first one here corresponds to the number of cubic feet, the space available, and x plus y greater than or equal to 50 means we have to make at least 50. So at least 50 refrigerators must be sold each month. And reducing these, this is 3x plus 2y less than or equal to 120. Here is the feasible set. Now this one is a little bit different than before because the direction of this inequality is going the other direction. It's bigger than or equal to. So on this one, the x plus y equals 50. Instead of shading everything above it and then getting this polygonal region here, we shade below it, and so we get this little slice over here. So the feasible set here is pretty small, just a really thin slice over there. There's only 3 vertices. It's a triangle. The y-intercepts here are 50 and 60, so those are the 0, 50, 0, 60. Plug those in, you get 7,500 and 9,000. But there's this other point here where these two meet. If you can solve the system of equations, you'll get x equals 20, y equals 30. So 20 and 30, 20 large fridges and 30 small fridges will give us 9,500, which is the largest of these. So that's going to maximize the profit. $9,500, sell 20 large fridges and 30 small fridges. And the last problem, this is the only problem that had an unbounded feasible set. Making chocolates, you got 2 plants. The main thing that I hope was clear here is it's the number of days that each one of them is going to be producing, and one of them can produce a certain number of days, the other one could produce a different number. It's not like they had to produce the same number of days, although that turned out to be the case. So I'll give you a second to pause it and read through the problem if you need to. Okay, we're trying to minimize cost here, so this is a minimum one. On the maximum ones, you often get a bounded set, feasible set. On the minimum ones, you often get an unbounded. Not always, but that typically happens a lot. So if we let x and y be the number of days Wichita and more producing, you can organize the data in a table like this. Wichita makes 3,000 pounds of semi-sweet and 2,000 pounds of milk chocolate, and costs $1,000 a day, and more, 1,000 pounds, 6,000 pounds, 1,500. And the requirements, we need to fill an order. So when you're filling an order, that means we're going to figure out how much semi-sweet chocolate is going to be made, and that has to be greater than or equal to 30,000. How much milk chocolate has to be made? It has to be greater than or equal to 60,000. Our objective function is the cost here, not the profit or revenue. It's a cost. So how much does it cost? Well, if it's $1,000 a day at the Wichita plant, then if the Wichita plant goes for X days, it's going to cost 1,000X. Wichita, 1,500Y at more. The constraints then are going to be 3,000X plus 1,000Y. Now that's how much semi-sweet, how many pounds of semi-sweet chocolate you make. You have to fill the order, so you have to have at least 30,000 there. And for the milk chocolate, this is the amount of milk chocolate you make in pounds, has to be at least 60,000. Usual xy bigger than or equal to 0. Reduce these two. So notice it's going to be much easier if you cancel common factors here. You get really nice inequalities, 3x plus y, x plus 3y. And if you graph those, you get a feasible set that looks like this. So these are the, this is a 3x plus y equals 30, x plus 3y equals 30, and then the two of them meet here at the point, if you solve these two equations, they meet at 7.5, 7.5. And because the directions of the inequalities are all greater than or equal to, we end up shading underneath or below all of these lines, and it's in the first quadrant. So we get a feasible set that's kind of got these three vertices, but it's bounded by the y-axis and the x-axis as well. So there's only the three vertices to find, and unsurprisingly, the minimum cost is not going to happen when you are just producing all at one plant. So it kind of makes sense that if you just produce at one plant and not the other one, that's probably not going to be a way to minimize the costs. You're going to want a mixture of the two. And that happens at the 7.5, 7.5, minimum cost of $18,750 when both Wichita and Moore produce for 7.5 days. So I hope these three problems were helpful. They're very representative. They kind of covered all the different types, or a couple bounded feasible set, another one unbounded. But these are really representative of the kinds of problems you'll see both in converting from the word problem to setting it up, as well as finding the feasible set and substituting into the vertices to find the maximum or minimum. So, hope these problems help. Email if you have any questions before the exam. And hope you had a good break, and I'll see you next week.